Howdy y'all, welcome to SimLab CFD training. The objective of this first tutorial is to get familiar with SimLab GUI and the CFD workflow. We're gonna have a simple manifold where water as a working fluid is going at 2 meters per second and exit with 4 outlets. In the learners folder, we will have files, and then we're gonna go to the first workshop where you're gonna have the input files. This is where the cat file is located, and the project is gonna be our working folder. We can simply import the cat file by grabbing and dropping it into SimLab. Leave everything as default. We can change the view here. So the first step of CFD workflow is that we need to create a surface mesh. For this example, we're not going to place any surface mesh control or any volume mesh control on the body. We just simply mesh the cat body as is. So I will choose the average element size of 10 millimeters for this example. And you can actually play around with the maximum angle per element. The smaller the number of these boxes, the finer the curvature of the CAD file going to be refined. So I'll do two examples where I'm going to put the 45 degree for this one, and then the next one I'll do 10 degree to see, so that you can see the difference. So this is the 45 degree one. And I will hide this and remesh the cat so that I can put it as 10 or 15 degree. So the same average elements mesh size, and I will put this as, let's say, 10 degrees so that the difference can be exaggerated. Let's create a new mesh in a new model. So this is the 10 degree one. So comparing two mesh, the 45 gonna have much coarser curvature refinement comparing to the 10. It's one meshing parameters to keep in mind. For this example, I will use the 10 degree maximum curvature angle. Click on the surface mesh and then delete the 45. Okay, now we need to CFD mesh this surface mesh. We're gonna go into, still in the same meshing panels, we're gonna go into the right, and then we will see the CFD mesh icon. The fluid body, I will choose my surface mesh. And then I would need to ignore the battery layers on the inlet and 4 outlets. For battery layers parameters, so I'll typically the first layer thickness factors is going to be anywhere between 0.1 and 0.15. The total number of layers, it usually is going to be between 6 or 8, and then the growth rate is usually between 1.2 to 1.3. But then how do we decide which numbers we're going to use in these panels? The most important thing about meshing for AgroSolve is that we need to ensure a smooth transition between the final battery layers to the free elements. So assume that the surface mesh size have the same size with the volume mesh, which means that this is going to be 10 millimeters. We can pull up our calculator and type in the following formula. So the first layer thickness factor is going to be 0.1, and then we multiply by the growth rate. Let's say this is 1.2, and then raise it to the power of the number of layers. So say 6. So at the first layer thickness factor of 0.1, growth rate is 1.2, and then 6 layers. The final battery layers is only about 30% of the free element. So which means that we need to increase this. We need to increase either any of these three numbers. So, but still we need to ensure that the y plus value is accurate so that we can capture the near wall velocity profile. So I will keep the first layer thickness factors the same. And if I increasing the growth rate to 1.3 and then using 6 layers, still the final battery layers is still 50% of the free element. We would target this somewhere anywhere between 60 to 70. So let's do 0.1 times 1.3. So at 7 layers at the growth rate of 1.3, this is good. So let's go ahead and use this number. Total number of layers is going to be about 7. Going to be 7. Growth rate going to be 1.3. We don't have any mesh control to transfer from the CAD. And then under advanced option for battery layers, you can choose if the battery layers type is going to be prism or TET. I will choose TET for this example. Click OK to start the meshing process. When meshing has been completed, we can inspect how's the transition between the final layers and the free elements. So this is our final layers of the battery, and this is our free elements. We don't have a steep change in element size, so that is good. So previously I was having about 62%. It would be better if I increase it to 70, about 70, to 65 or 70. It would be much smoother, but it is good already. Okay, so before doing the flow setup, we also need to inspect the 3D elements inside. So let's position our model this way, and let's create a section cut in the Z normal direction. Let's position it like this in the middle so that we can see a nice, we can have a nice view of the mesh. So you can see that we don't have a steep changes in the transition between the final battery layers and the free text element. So that is good. And we can also see how the battery layers being wrapped around the corners and the curvatures. You can also change the section cut or the slice plane to the X normal direction so that we can see the mesh at the outflows. Okay, we have nice structure mesh to capture all of the flow resolution. Okay, so the mesh is good. Now let's go back and do our flow setup. We're gonna go into the solution, choose flow solution to start our flow setup. The bodies, I will import the fluid. Flow type gonna be turbulence. Turbulence gonna be SA, but this is the list of turbulence model you can use in AcuSolve. We don't have heat transfer for this example, so we're gonna turn it off. Click OK. For this problem, we will have water as our working fluid, going in at 2 meters per second and exit at 4 outflows. We will start by going into material and then click on built-in material database so that we can import water, the working fluid, into our material and properties browser. We already have imported it here, but I can still do it again. So if you go into fluid and go all the way to water, so you have built-in properties here. What you would do next is that to load it into the material browsers. I already loaded it in, so it won't let me load again. But if this is the first time you use SimLab, you will see that water will be populated in the material browser. Okay, we can assign the material to our working fluid by right click and then click on material, and it will be water. Or you can simply, in the assembly browser, just click on the drop down menu and then there's going to be a list of materials you can add. Okay, so let's assign inlet condition for the inflow. I'll pick this phase. And let's change the unit from mmks to mks. Inflow type. So this is the list of inflow type you can use for AcuSolve. So you notice that velocity and average velocity. So what is the difference between these? So velocity is that you meant to prescribe a constant velocity at the inlet. For average velocity, you are prescribing a profile of the velocity. This is great for assigning a fully developed flow at the inlet in certain problems. And then the profile is going to be parabolic with the average velocity as assigned. So I'll use average velocity, and I will set I'll set it to be 2 meters. Click OK. So our inlet is done. Now let's do the 4 outflow. I'll call this outlet number 1. It is not recommended that you put all 4 phases into one outlet set. So first of all is that we also want to see the mass flow rate or velocity for individual phases. So putting all 4 into one set, you won't be able to see that. is outlet number 2, outlet number 3, and outlet number 4. Okay, so settings, if you right click on setting, you will see that we have many solver settings here. The most important one is the relaxation factors. This is where you change the relaxation factors and enable the flow or turbulence or heat transfer equation depending on what you want to do. I will go over that in the next tutorial. This is the convergence tolerance. It is set to be 10 to the negative 3 as default for pressure, temperature, and velocity. And for turbulence properties, it's going to be 1 order of magnitude higher. For this simple problem, we don't need to change anything, so just leave it as is. Result request. This is where a result request is useful where we're setting up a transient simulation, especially the nodal output. So the nodal output frequency and the nodal and the output time interval specify how frequent you want to write out the results. And the most important thing is format and execution option. This is where you specify the number of processors dedicated for solving. So the default you will see in SimLab is going to be 8, but I will use 20 cores for this example. The question is why 20 cores? So in my computer, I have total numbers of cores is going to be 28, but the physical cores is only going to be 20. We never want to hyper-threading AcuSolve, so which is the reason why I would never go over the number of physical cores. If you put 22 or 21, it will solve slower than 20. So just keep in mind how AcuSolve react with hyper-threading. So let's save our database before we get to solving. We will save it into our project folder. Let's name it Manifold. Okay, when everything is ready, we can right click on result and click update. So started solving. You can take a look at the log file where the solver record all of the solving process. And you can take a look at the residual by going into plot convergence. Let's wait for a few minutes because it needs to go into the first time step before we can plot convergence. Okay, so it's going to first time step, which means that we can go to plot convergence now. So AcuProbe going to be opened up. For AcuSolve, which is the finite element method, there is 2 types of residual criteria you need to pay attention to. So first of all is the residual ratio. So the residual ratio represents how close your solution is comparing to the Navier-Stokes equation. And the solution ratio, the next one is going to be the solution ratio. Solution ratio represents how stable the solution is over time. So for the convergence criteria for residual ratio, as I mentioned before, is going to be 10 to the negative 3. And it's going to be 10 to the negative 3 for velocity, pressure, and temperature. The turbulence parameters, the eddy viscosity, it will be one order of magnitude higher at 10 to the negative 2. And the solution ratio, the convergence criteria, is going to be always 10 to the negative 2. If the solution ratio is below the convergence criteria, which is 10 to the negative 3, and the solution ratio is not, it can simply means that the flow is inherently transient, and we would need to use transient simulation to properly resolve the flow field. Okay, let's wait for a few more minutes so that it can solve, and we will go right back. When it's done solving, this panel will appear. We will use multiphysics post-processing for now. Let's take a look at the log file, as I wanted to show you something. Scroll all the way to the bottom. You will see that this solution is never converged because the time step reaches 100, and the eddy viscosity residual ratio and the solution ratio is nowhere converged. I want to point out that this happened a lot where you have inflow and outflow boundary. So this causes the solution to be unstable, and the solution is really hard to converge with this condition. So what we usually do at Altair is that we would enable the backflow condition and set it to be area average, and this will greatly help with the convergence in case you want to rerun the simulation to reach the convergence point. Okay. In this multiphysics post-processing, I want to show you how to do certain operation to get the parameters of interest that you want. So let's start by creating a section cut in the Z normal direction. You see that because we prescribe an average velocity, which means that velocity at the inlet is going to be parabolic, you see a nice profile going in at the inlet. And if you want, we can change the contour into vectors. So instead of, let's choose the parameters we want to display to be velocity. And the plot going to be vectors. And let's change the scale into uniform. Let's do 0.4. So you will see the vectors representing the flow field. And let's put the section cut in the X normal direction. And it is gonna slice one section only. If you want to switch it, you can switch it here. So we obviously have some backflow condition at outlet number 1 and outlet number 2. Let's turn off the vectors and let's go into the results and create a streamline. Let's create a rig, gonna be the planar surfaces. Not sure if this gonna work. And let's put the number of seats to be 200. Click the add and then create streamline. Okay, so the streamline have been created. We can also display vectors on the streamline so that we know the direction. Okay, let's close this. The next question is how do we get the parameters at the inlet and 4 outlets? We can do that by again going to the plot convergence. So AcuProbe will pop up, and in the surface output, let's suppose that we interested in the mass flow rate of the outlet, right? So we're gonna go into mass flux and create plot. You see that it's not really stable solution because of the backflow. But if you want to export this number, simply right click and click export. You can export as XML file or raw data or raw text data. So let's say this is outlet number 1, mass flux, mass flow rate. If you have other parameters of interest, such as pressure, you can do the same operation where you click plot and then you click export. But let's take a look at the file we just wrote out. So this is our data file for outlet number 1. And because we are doing steady state, we only interested in the last numbers. Okay, so that is the formal way to do it. But what if you you don't want to do any of those operations, clicking on AcuProbe and then click on the individual surfaces and then export? There's a quicker way to do it where we're going to use SimLab directly. When you right click on results and click on response, we can click on mass flow rate and select the phase of interest. We'll name this as mass flow rate outlet 1. Click OK, and you will get the mass flow rate at the outlet number 1. You can do the same for pressure. We don't have temperature here, but we can do pressure and velocity magnitude. The value you can do average, maximum, minimum, and this is what we get faster than AcuProbe. But now let's try for outlet number 4 to see what we got. We will go into response, mass flow rate, outlet number 4. We got 10 times more mass at outlet number 4 comparing to outlet number 1. We can take a look at pressure. So the pressure is 1 Pascal. So in this response, we can only get this much. So if you want to get a lot more complicated parameters, you must use AcuProbe. But for the response, this list is exhaustive. Okay, so that's it for this tutorial. I hope you find it helpful. I will be covering conjugate heat transfer application in the next 2 workshops. Thank you. Howdy y'all. Welcome back to SimLab CFD training for AcuSolve. The objective of this second tutorial is to show a general workflow for conjugate heat transfer simulation in SimLab. We will use a stainless steel mixing elbow for this tutorial, and for the problem, we will have 2 inlets and 1 outlet. The smaller inlet have water entering at 1.2 meters per second at 320 degree Kelvin, and the larger inlet has the velocity at 0.4 meters per second at 295 degrees Kelvin. We will also apply a convective heat transfer for the outer wall. Let's start with SimLab GUI, and we can import the geometry from the input file of the second tutorial, mixing elbow steady state. Simply drop the CAD file into SimLab and it will automatically import it. So we have the elbow, but we don't have the fluid domain yet. So we need to create the fluid domain by going to geometry in the create. So there is fluid domain, and we can create the fluid domains for this problem using 2 ways. So first of all is the body based. We simply click on the elbow and click OK. You will notice that there is going to be a bunch of fluid created. So we're going to hide the main one. So the biggest one is the one that we want to reuse. We will hide it. And then we simply delete 4 other ones. And we have the fluid and the solids. So that's one way to do it. I will delete this one, and I want to show you the second way to do it. Again, go into create and fluid domain. We will create the fluid domain by using the wetted faces, which means that we have to select all of the internal faces of the elbow. We will select and click on select adjacent layers. The guide face, I will select, just choose any of the internal faces as a guide face. The limit face, I will select the outlet, the inlet, 2 inlets. Click apply. We will inspect if the selected face is the one that we want to use. Click I to isolate. So these are the wetted faces that we use to create the fluid domain. Click on Create Fluid Domain again, and where it faces, Windows select everything, and click OK. So we will have the fluid domain created, the fluid body created. So two ways to do it. There is four ways to do it, but I typically use these two. Now we can start applying some mesh control at the important region, especially the mixing area where the smaller inlet meet the larger inlet. I'm going to go into mesh and click on mesh control, and we want to apply a regional mesh control at the mixing region. Let's create the cylinder. On the section cut in the Z normal direction, and I want to position the regional mesh control to meet this arc right here. Snap to the arc, and then I want to increase the diameters of the cylinder. About this is enough. Click OK, and I will have the refinement zone of 4 millimeters for this zone. Click OK, and I want to apply this mesh control to both the elbow and the fluid. I will also apply a phase mesh control on the two inlet faces. We can also pick this one. And let's put this to be say 5 millimeters, because we do want at least 3 or 4 layers to capture the conduction between the solid and the fluid. Let's do 3. Because this is the conjugate heat transfer application, where the heat is going to be conducted from the fluid to the solids, which means that we have to create a connecting mesh at the interface where the two materials meet. I'm going to go into geometry and Boolean these two bodies together. Now we Boolean combine and make sure the created connected bodies is enabled. Otherwise, they will be fused into one single solid. So for the surface mesh size, I will choose 8 millimeters. And then I will choose 15 degree as maximum angle per element. Click OK to start the surface measure. Okay, so we have three surface mesh layers for the solids, and we also have we don't have three surface mesh layers. This happen for some reason the surface layers isn't respected. We can fix this manually, but first we need to unmerge the two body. We can fix this by using the change layers option. We can change the number of layers to 3. Click OK. So we have a clear refinement zone here, where the outside of the refinement zone is going to be 8, but inside is going to be 4 as we set before. So we only apply the surface mesh control so that the surface have 3 layers, but we need to do an additional step where we set the volumetric layers to be 3 too. So it's going to be 2-step process, one for the surface and one for the volumetric elements inside. We're going to pick the elbow, and then the number of layers is going to be 3. Click OK. And we also need to transfer the regional mesh control from the CAD body to the surface mesh bodies, so that we can also apply the regional mesh control to the volume mesh. So I will unselect and then click on these two bodies to transfer the mesh control from the CAD to the surface mesh. Click OK. So we have applied the regional mesh control, and we also set the volume layers to be 3. We are ready to CFD mesh this model. Click on CFD mesh. The fluid is going to be the fluid bodies. We want to ignore battery creation on the inlet faces and the outlet. The solid body, I will choose the elbow. Fraction of the mesh size, I will use the same parameters. With the first layer thickness, going to be 0.1. Total number of layers is going to be 7, and the growth rate going to be 1.3. And I will set the average TED element size to be 8. Because I have manually transferred the mesh controls from CAD to the surface mesh, as I mentioned before. But you can also use the automatic box here to transfer it in the background. Click OK to start the measure. So the meshing have been completed, we can start inspecting the mesh before we do the flow setup. Okay, we have a nice transition between the final layers of the battery to the test elements. Something happened here. We can reset the model. So this is the final layers of the battery, and this is the free elements. You can see that we don't have like a steep changes between those two, which means that the mesh is good. This is the inlet. We have three layers, three conduction layers on the surface. And let's look at the outlet. Again, no steep changes between the final layers of the battery and the free test element. We can turn on the section cut to see the 3D elements inside. And we turn on the section cut in the Z normal direction. Okay, we have three volume layers for the solids so that we can capture a conduction temperature profile. We see that the regional mesh control is being respected. We can clearly see the changes of the element size from the free test element to the refinement zone. And of course, again, we don't have a steep changes between the final layers of the battery and the free test elements. So 3 layers on the surface and 3 layers on the volume, in the volume. Okay. So the mesh is good. We can go ahead and do our flow setup. We're going to go into solution and click on flow. And we will select these two bodies, the elbow and the fluid, for our CFD. Physics going to be still incompressible. Flow type going to be turbulent. And turbulence model going to be using SA. But for this example, we will enable heat transfer. Click OK to create the solution. For this problem, we will have two inlets. The smaller one have water coming in at 1.2 meters per second. And the larger inlet gonna have water coming in at 0.4 meters per second. And we have one outlet. So we're gonna go into inlet battery condition. And let's set the smaller inlet. I will select this phase. In flow type, I will use a constant velocity of 1.2 meters per second and a temperature of 3.8 degrees Kelvin. Click OK. I will also set the apply the larger inlet. Velocity, I will keep the same with the normal velocity of 0.4 and the temperature of 295 degrees Kelvin. For the outlet, it's just simple outflow condition. And we will also set a convective heat transfer coefficient for the outer wall. It's going to be wall, and we name this to be outer wall. And I will select all of the faces, all of the outer faces. Okay, it's going to be convection with the heat transfer coefficient of 20 and the reference temperature of 295. Click OK to apply changes. We don't need to change anything in the solver setting. And the result request, we don't need to change anything in the result request either, at least for now. And for the format and execution option, I will still using toning processors for this tutorial. And let's save our database before we run the simulation. Let's go to the second folder, project, and let's name this to be mixing elbow, steady state. I should rename the flow to elbow steady and save the database again. Last but not least is that we will apply the material on our bodies. So we can go back into material and built-in database, fluid. If you have not imported water, you can click on to load to material browser here. And then the pipe is going to be stainless steel. So we're going to go into solid and look for steel or stainless steel. We use steel and we load it into the material browser. I already loaded it, which means that this panel is going to appear. But if you have not, in the material browser, steel will be populated in the solid. Okay, I will set the material to be steel for the elbow and water for the fluid. When everything is set, right click on results and click update to start the solver. When the solver starts the very first time step, you can right click and go to plot convergence to launch AcuProbe. And this way you can monitor the residual ratio and the solution ratio. Okay, let's wait for it to solve and then we will be back later. Okay, when it's done solving, please choose multi-physics post-processing. And let's take a look at the convergence. Click reset. So as I mentioned before, the convergence criteria for the residual ratio for temperature, pressure, and velocity is going to be 10 to the negative 3, which is right here. And you see that the solution stopped at 25th or 28th time step when it go below the convergence. And the additive viscosity is 10 to the negative 2, which is right here. And we also need to take a look at the solution ratio to check if it's go all the way down to 10 to the negative 2 for all properties. So I can see that is converged really well. Now let's go back to our SimLab for our post-processing. Okay, let's position it in the XY plane. Now let's create a section cut in the Z. And you can see how the mixing happen, where the large inlet meet the smaller inlet. This is just a display issue. Let's put it this way and get, okay, then it's gone. So this is where the mixing happen, and we have a nice layers. We have enough layers to capture the conduction inside the solids. The temperature gradient is right here. This is temperature, and we can set it to be vectors to see the flow field. Let's put 0.2. So this is how the flow field looks. We have some recirculation, some small recirculation here. Then moving forward to the outlet, the recirculation gone. Okay, so we have some so we have temperature outside, and we can get the average temperature of the outlet by going to response, click on temperature, click on the phase, click on average. So the average temperature is 298. And we can take a look at the pressure at the inlet. So about 35 Pascal. Okay, so for the smaller inlet, it's going to be 156 Pascal. So this is the fast way to do it. You can always go back to AccuProbe and click on the surface output to get the properties that you want. This is the pressure at the smaller inlet. And for the large inlet, we can get the pressure. And then we can export it. to the text file or XML file. The next question for conjugate heat transfer that new users always ask is that how we can get the convective heat transfer on the interface between the fluid and the solids. SimLab have an automatic way to do it, but then you would need to plan well beforehand. So I will detach the result out of this solution. To do that, you're going to go into result request, go all the way to the bottom. This is where you specify the heat transfer coefficient output. The default you will see is going to be turbulence wall. If you want to get the heat transfer coefficient using the reference temperature, use the drop-down menu to select the reference temperature and select the reference temperature of 295 degrees Kelvin. Click OK. And then we're going to rerun the simulation. That's why you need to plan well beforehand. After the solving is complete, we're going to go back into multi-physics post-processing. The solution is going to be the same as before. We just add the result request where we want to calculate the heat transfer coefficient using the reference temperature of 295 degrees Kelvin. So the parameters is going to be surface film coefficient. Now let's hide the elbow and adjust the legend. I want to set this to be 100. It could be that the reference temperature we choose in the result request to be 295, it is too close comparing to the average outlet temperature of 298, which is the reason why the heat transfer coefficient is really high, and it's really hard to set the legend correctly, but the workflow is there. Whenever you want to request the heat transfer coefficient, please do it before you run the simulation. So that's concluded the steady-state conjugate heat transfer workshop. Next, I will show you the frozen flow approach so that we can see how the temperature contour changes over time without rerunning the entire Navier-Stokes equation. Thank you. Howdy y'all! Welcome to SimLab CFD training. The objective of this third tutorial is to demonstrate the frozen flow approach with AccuSolve. We will be using the same model and the mesh generated from the second tutorial. But for this problem, the temperature of the inlet will both change to 283 Kelvin, stay there for 1 second, and bounce back up. The frozen flow approach is the best way we can solve the energy equation separately from the mass conservation and momentum equation. Let's start with where we left off from the second tutorial. The same model, the same mesh. I will hide results. And in files, I will save as to create a new SimLab database file. I will duplicate this solution. and rename it to be elbow transient. The type I will switch to transient. And the mesh will be using the same setting. I will go back to the time step and the final time later. I will still using 20 cores for the solving. In the problem description, everything stays the same. The only thing that changes here is the temperature of the two inlets. For the larger inlet, it bounced from 295 to 283 and then stayed there for 1 second and then bounced back up. And the changes happen within 0.2 seconds. And the same for the smaller inlet. The temperature changes from 320 to 283 and then stay there for 1 second and bounce back up. And the changes also happen within 0.2 seconds. You'll see that it will, at 0.4 second, it go down, and in the middle, which is 0.6, and then stay there to 1.6 seconds and bounce back up. Everything return to normal at 1.8 seconds. Okay, let's close this, and we will change our boundary condition. Let's delete all of the response in the elbow transient. Now let's do the smaller inlet. So the initial temperature is going to be 320 degree Kelvin. I will set this to be 1 Kelvin. Create a new multiplier function. I will call it to be small inlet multiplier. It's going to be piecewise linear. The curve fit variables is going to be time. And let's create new curve fit value. So at 0 seconds, it's going to be 320. And it stayed there to 0.4 seconds. So 320. And at 0.6 seconds, it go down to 283. It stayed there for 1 second to 1.6. And bounce back up to 1.8. 320. And it stayed there for the rest of the flow field. I will set to be 4 seconds. 320. Click OK. So this is my multiplier functions. I can set the multiplier function this way because what AccuSolve does in the background is that it's going to take the value that we input here, which is 1 degree Kelvin, and multiply it by the multipliers 320. So 1 multiplied by 320 is still 320 degree Kelvin. If you don't want to change the temperature to 320 degree Kelvin, you would need to take out the calculator and do 283 divided by 320. It will give you 0.884375 here. And what you do next is copy this number and then paste it here. You still need to keep the temperature of 320, right? Because 320 multiplied by 0.884375 is going to be 283. But that is a long way to do it. That's my least favorite way to do it. I prefer that, okay, I'll set the temperature to be 1 degree Kelvin and set my multiplication to be the numbers, the targeted temperature numbers. Click OK. OK again. And we're gonna set the multiplier function for the large inlet. Let's change this to 1 Kelvin. It's going to be piecewise linear. Curve fit variable is going to be time. And I will create the new curve fit values. So in the problem description, it jumped from 295 to 283. 0 to 95, 0.4 to 95, and at 0.6 seconds, it's jumped down to 283. Stay there for 1 second. It's 283. Jump back up to 295 and stay there for the rest of the flow time. So this is my multiplier function for the large inlet temperature. Again, 1 Kelvin multiplied by 295, that is 295 degree Kelvin. If you don't want to change the temperature to 295, you would need to do 283 divided by 295, and it is so whatever this number go out, you put it to the multiplier function where the temperature is changed to 283. Click OK. Because this is the frozen flow approach, and the only thing changes is the temperature. So in the server settings, I will disable the flow and the turbulence equation. Only leave the temperature equations on. AccuSolve will only solve for one temperature, and it will use the flow field from the elbow steady run. I will initialize the transient run using the elbow steady state solution. And for the result request, let's suppose that I want to output the node. I want to output every 1 time step. I will set this to 1. If you want to output every 2 time step, you set this to 2, and so on and so on. I'll set this to output every 1 time step. Click OK. And for the time step size, I noticed that my multiplier function changes from within 0.2 seconds. So my time step size, I will choose it to be less than 0.2 seconds. I will choose 0.1 for this example. And the final time, I will choose it to be 4 seconds. So 4 seconds of flow time, and the time step size is 0.1. So which means that I'm solving for 40 time step in total. And my result request is that I write out the output for every 1 time step, which means that I will have 40 time step available for post-processing. Okay, so when everything is ready, I have switched my solution from steady state to transient. I have changed my time step to be 0.1 seconds, and the final time is to be 4 seconds. I have disabled the flow and the turbulence equation, and only have the temperature equation enabled, which is what I want for the frozen flow approach. So there is the minimum and the maximum stagger iteration I want to mention. So this is the numbers of iteration needed to run one time step. The default is going to be between 2 and 4. The default numbers is fine. So, but in certain transient simulation where you have a really large change between the time step, you can increasing the max to be you can increasing the minimum to larger than 2, and then the maximum stagger iteration to be larger than 4. Usually it's somewhere between 4 and 6 is optimal. I will leave it as default. Format and execution option, I will still using 20 cores for my simulation. I have initialized the transient simulation using the previous result, using the flow field from the steady state run. And I have put the inlet multipliers function for both large and small inlets. Whenever I'm ready, I will save the database and right click on results and click update. In the solver log, when it go into time step, you will see that only the temperature equation is being solved right now. And when you look into the plot convergence, again, only one residual ratio is being displayed, which is the temperature. Now let's wait a few more minutes so that it can finish solving for 4 seconds of flow time. When the solving has completed, let's choose multi-physics post-processing. And let's change this to be this time. So this is the initial condition. And again, we use the steady state flow field to initialize the transient. So the initial at time 0, it is the steady state solution. And at this moment, the temperature changes. It's jumped down to 283 Kelvin. And then stay there for 1 second. Let's jump back up to the regular, to the initial temperature. And you can see that it does take some time so that the conduction can switch back to normal. And we can animate this result too. Just make it go slower. We can export the animation. Let's put it back to go to the first time step. And then there is going to be the little play button here where we can record the animation. We can save it as animation. And the MP4 file should be written. and you can play it locally using your media players. So let's suppose that our parameters of interest is how the outlet temperature changes over time. We can go into plot convergence and retrieve that. Let's say surface output and outlet and temperature plot. So this is how the outlet temperature changes over time. You see that the outlet temperature does drop when the inlet temperature decreases to 283, and then after that it bounces back up. We can export this as a raw data file with label, and let's see, I will name this to be outlet temp versus high. And this is my data file. So at this moment, 0.6 seconds, the temperature drop, and then it bounced back up again. And that concluded our conjugate heat transfer workshop. I hope you find this tutorial helpful, especially how to use the frozen flow approach to solve the energy equation separately, because it will come really handy in the future, especially dealing with heat transfer application. Thank you.